training webinar. I'm Lisa Matthews with EPA's Office of Research and Development. And today we're going to have a presentation on EPA's Watershed Management Optimization Support Tool. We call it WMOST. WMOST is a decision support tool to facilitate integrated water management at the watershed and community scales. It allows users to determine the most cost-effective suite of wastewater, drinking water, stormwater, and land conservation management practices to meet both water quantity and water quality goals. It allows users to assess the effects of stormwater control measures, non-structural stormwater measures, agricultural conservation practices, riparian buffer restoration, land conservation, water conservation, repair of infiltration and inflow to sewer lines, improved wastewater treatments, water reuse, and aquifer recharge. Today's webinar will provide an overview of new WMOST capabilities and a demonstration of how to import data into WMOST, run optimizations, and review results. And we will also have some case studies about how the tool has been applied in different states and watersheds. So if you have a science question during or after the presentation, please type it into the Q&A window at any time. And once the presentation ends, we'll answer as many questions as time allows. You can listen through your computer speakers, and we plan to post the slides from today as well as a recording to our website within the next 2 weeks. So with that, I want to go ahead and introduce our presenter today, Dr. Naomi Detenbeck. Naomi is with the Atlantic Coastal Environmental Sciences Division within the Center for Environmental Measurement and Modeling in EPA's Office of Research and Development. Thank you, Naomi, for your presentation today, and I'll turn it over to you.
Thank you, Lisa, and thank you everyone for joining us for this presentation. As Lisa mentioned, I'll be discussing a suite of tools associated with our Watershed Management Optimization Support Tool, or WMOST for short. I'll start out by talking about the importance of integrated water management and provide an overview of the tools we've developed to facilitate integrated water management. Then briefly review the processes for loading data into WMOST and using it to look at the effects of stormwater control measures in reducing stormwater runoff and pollutant loads. I'll briefly go over 3 different case studies, ranging from agricultural to highly urbanized watersheds across the country. Talk about 2 interpretive tools for comparing the results across multiple scenarios with WMOST. Talk about how the results are being used by communities and watershed organizations, and finish with some take-home messages. So when we started out to develop WMOST, we were trying to address a series of problems that many communities and watershed organizations were facing. First and foremost, stakeholders need to find the most cost-effective management options to meet multiple targets for water quality and water quantity at the small watershed and community scales. And by small watershed, I'm referring to 12-digit to 10-digit hydrologic units. The targets can include things like water quality criteria, loading targets for total maximum daily loads or alternative TMDLs, meeting consent decrees for combined sewer overflows, minimizing or preventing floods, or maintaining sustainable water supplies, minimum flows to support aquatic life use or water reuse. We're also interested in encouraging application of an integrated planning framework. So rather than looking at each program in a stovepipe fashion, looking across stormwater, wastewater, drinking water, and water reuse, as well as conservation and restoration programs. Many people are interested not only in the immediate benefits of these management actions in meeting the water quantity and quality goals, but also looking at ancillary benefits, both related to water quality as well as non-water quality co-benefits of the management actions. And I'll talk about some approaches we've used to apply values estimate values for these additional benefits. And then finally, we're planning not under static conditions, but in the face of land use change and climate change. So how can we identify strategies that are robust, not just for current conditions, but also future conditions? We've devised an approach for phasing our tool development process, starting out with development of WMOST as the backbone for the suite of tools. The tools are built on a Microsoft Excel spreadsheet, which most people are familiar with. WMOST is the backbone of the structure that helps you to organize your available data to analyze the problem of interest. WMOST prepares files to be uploaded to a NEO server, which provides which is the powerhouse for running the actual optimization problems. We've developed WMOST to have linkages to many other commonly used tools and models. So for example, we can take outputs from many common watershed models such as SWOT, SWIM, or HSPF, preprocess those through a hydroprocessor to format them for input into WMOST. WMOST also takes advantage of EPA's existing stormwater management model and SUSTAIN, which is just an interface for SWIM, and interacts with these behind the scenes to estimate the effects of stormwater best management practices in reducing runoff and pollutant loads. WMOST can also take advantage of outputs from FEMA's hazards tool in the flooding module to construct a flooding risk cost table to estimate risk and costs associated with floods of different recurrence intervals. We also can interface with another EPA tool called LASSO, which stands for Locating and Selecting Scenarios Online, which allows you to examine multiple climate change scenarios and identify a bounding box to describe the range of possible future conditions, and then run multiple WMOST scenarios with our hydrologic comparison assessment module. And then finally, we've developed some aids in interpretation of results and comparing different scenarios, including ScenCompare and our benefits module. This is another way of looking at that same information, starting out with the preprocessor to process outputs from common watershed models. This produces time series for runoff, recharge, and pollutant loads, which are imported into WMOST. WMOST is interacting with SUSTAIN or SWIM behind the scenes. We can also take the inputs from the hazards tool for the flooding damage table. The outputs from WMOST are uploaded to the NEO server with online optimization programs, and then the results from NEOS are imported back into WMOST and displayed in the forms of tables and graphs. I mentioned that WMOST is built on a Microsoft Excel interface. It's currently configured to work with the 32-bit version of Microsoft Excel, which used to be the default version installed. Just recently, Microsoft switched to using the 64-bit version as a default for installation. You can actually install either version regardless of whether you have a 64-bit computer or not. We do have updates for the 64-bit version of Excel in progress, but we've tested WMOST on 2010, 2013, 2016, and Office 365 versions of Excel. This is the front page of the interface. You start out by choosing the type of model you want to look at. You can just look at hydrology or a combination of hydrology and pollutant loads. You then go through a series of data input screens, run the optimization, and finally review results in the form of tables and graphs. We refer to WMOST as a partially lumped model. So rather than characterizing every square inch of a watershed and modeling those separately, we lump similar areas based on land use and soils to constitute something we refer to as a hydrologic response unit. So for a given amount of precipitation coming in, for a given combination of soils and land use, you'll get a characteristic time series of runoff and recharge. and there'll be a different time series for each hydrologic response unit. There are a number of ways of getting data, these time series into WMOST. We have pre-processed some existing watershed model outputs, mainly for the New England area, and those can be automatically imported into WMOST via a query over the internet. And I've shown a screenshot from that portion of WMOST in the top of the screen. You start out by telling WMOST where your database inventory file is located on your computer, and then entering the name of the watershed of interest, the model type, the land use scenario could be past or future scenarios in some cases, climate scenario, baseline or future climate scenarios, and then a HUC 12 or HUC 10 of interest for the subbasin. You can also explore these data interactively via our estuary data mapper application. The URL for download is shown on the left there, and a screenshot of the interface is shown at the bottom of the screen here. So you start out by zooming into your area of interest using the first tab. So you can click on states and zoom to the state of interest, and from there zoom into a particular watershed of interest. If you go to the second tab, you pick the WMOST scenario and endpoints of interest and identify the HUC that you want to examine. You click retrieve and show selected data on the button near the bottom of this tab, and it'll pull up the data set of interest. In this case, I'm showing the hydrologic response units for a particular HUC 10 in Massachusetts. And then on the Save Data tab, you can choose to save the data in the form of shape files, ASCII grids, and CSV files for the time series, which can then be imported into WMOST for analysis. If you have other watershed models you would like to use as input, you can use our Hydroprocessor to format the time series for WMOST. And the Hydroprocessor handles output from HSPF or SWAT. So we just talked about using the baseline hydrology module to get data into WMOST, the initial time series for runoff, recharge, and pollutant loads before you have any management practices implemented. For both the baseline hydrology module and the stormwater hydrology module, you can either do this in automated fashion using the options on the left-hand side of the screen, or manually enter your own data using the options on the right-hand side of the screen, going to the tables and cutting and pasting from your data set into the templates that are set up by WMOST. So now I'm going to talk about the stormwater hydrology module using the automated fashion for defining the managed time series. If we click on this button, we come to this screen. We want to start out by importing the hourly time series, and we're going to run a daily model. WMOST can run either on a daily or monthly time steps. Because stormwater runoff changes relatively rapidly, we want to choose the daily time step. You can then select from a table with drop-down lists of various stormwater control measures. And I've zoomed into that here. You can model up to 9 different BMPs at a time. And the list of potential BMPs to include is shown at the bottom of the screen. With version 3.1 of WMOST, which will come out with HCAM, we also have green roofs added to this list. This also has a column for you to add the design depth of interest, which you can usually get. They're usually state specifications in the state stormwater guidance manuals. And then finally, a column for decay rate, which describes the rate of loss of pollutants within the BMP. For example, for nitrogen, this could be through the process of denitrification, converting nitrate to nitrogen gas, which then escapes into the atmosphere. The latter were pulled in from EPA's OPI tool and have been calibrated using data from the University of New Hampshire Stormwater Center instrumented BMPs. You can always override these if you have more pertinent data from your area of interest. At this point, you're ready to generate the input file source sustain by clicking on the button circled at the bottom. And you'll see a series of progress bars come up as the different files are produced. This usually just takes a few minutes. And then you're ready to run this actual stormwater model and populate the input fields. Again, you'll see a series of progress bars and then a message when the BMP simulation is completed. At this point, you'll be brought to a series of tabs for the time series, one tab each for runoff, recharge, runoff loads, and recharge loads. So these are unit, runoff, recharge, and loadings. For example, the runoff is in inches per acre, per single acre. In these tabs, you'll see both the baseline time series before any management practices have been implemented, as well as a series of managed time series. So each column here represents a combination of hydrologic response unit and best management practice. You can then proceed to the land use page to define the range of areas that you want to consider for implementation of the BMPs. And that's what this tab looks like. There'll be a table for each different BMP type that you entered previously. The names of the HRUs are pulled in from a table you've already imported in the second column here. And then you specify a minimum and a maximum area for application of the BMPs. This is actually the area of the land that's going to be treated by the BMP, not the area of the BMP itself. We then enter the initial cost to, it says conserve because we use this for conservation as well, but it's either to conserve or to construct the BMP. So it's a capital cost, as well as an annual operation and maintenance costs. We do have default cost data available in WMOST, but again, you can override these if you have more regionally specific values. And for example, you might want to use EPA's National Stormwater Calculator to estimate regionally specific cost values. I focused mainly on the urban BMPs in the first two modules, but there are a variety of management actions you can explore in WMOST versions 3 and onward, including land conservation, not just the urban BMPs, but also a handful of agricultural BMPs, some additional water quality BMPs like stream bank restoration and outfall enhancement to reduce erosion, some direct reduction BMPs like urban tree canopies or street sweeping, implementation of riparian buffers, a number of management practices dealing with drinking water and wastewater, including incentives for demand management for drinking water, enhancing septic treatments, adding storage for groundwater and surface water to meet drinking water demand, interbasin transfers of water, either bringing drinking water in or transporting wastewater out for treatment elsewhere, or infrastructure improvements to the wastewater treatment plant, water treatment plant, or aquifer storage and recovery system. So at this point, you've entered the baseline time series, developed your managed time series by estimating with the stormwater module, and defining existing infrastructure with associated costs and other management options you might want to consider. So at this point, you're ready to run the optimization module. So behind the scenes, WMOST is generating something called AMPL code, which just stands for a modeling language for mathematical programming. You don't have to understand the code. I'm just giving you some examples of what WMOST is doing behind the scenes. It's simply a way of describing an optimization problem. So with an optimization problem, you have an objective. In this case, our objective is to minimize cost. So the cost equation is simply the sum of all the demand management actions that you are considering. And then there are a series of constraints associated with the optimization problem. You're then ready to submit these files to the NEOS online server. And there are a lot of different algorithms available in NEOS. We use the Bone-Min solver for WMOST problems. So you go to the site. This is a free site, provides you a lot of computing power, so you don't have to have optimization programs installed on your own computer. You submit 4 different files to NEOS: the model file, data file, commands file, and options file. If you have a simple problem, you can get results returned within a few minutes. If it's a more demanding problem or there's a lot of traffic on the server, you may have to be put into a queue and wait for an email to notify you that the results are ready. And typically this happens within a few hours. At this point, you select all the material on the output screen, copy and paste it to a word processor, for example, Notepad, and save it. You then import the text file back into WMOST using the results module and look at the results in the form of graphics, tables, and you can look at calibration statistics as well to evaluate fit. I'm going to walk through 3 different case studies, emphasizing different aspects of setup and results. They're in different phases of completion. This first case study is still in progress. The Cypress Creek in Texas is located northwest of Houston in Harris County, a very densely populated county. It's also an area experiencing rapid growth. As you can see from the picture on the left, there were significant flooding impacts and damage associated with Hurricane Harvey, as well as earlier storms in the system. This is a concern not only for the local watershed residents, but also for downtown Houston, because the floodwaters actually overflow the watershed boundary to Addicks Reservoir watershed to the south. Addicks Reservoir was constructed to protect downtown Houston, but it's already near capacity, so adding additional floodwaters to it put the downtown communities in Houston at risk. There are also significant water quality concerns within the watershed that stakeholders wanted to address. So we worked with the stakeholders and described the capabilities of WMOST, and together we came up with a series of questions to address through application of WMOST. So first and foremost, they wanted to evaluate practices for flood mitigation and also see if those optimized management practices for flood mitigation would also benefit water quality in the watershed. Conversely, if we optimize management practice to meet water quality goals, are there ancillary benefits to reduce flooding? They're interested in looking at potential contribution of management practices at different scales, ranging from individual parcels and neighborhoods to more regional scale solutions. They're also interested in comparing gray versus green infrastructure solutions. So green infrastructure practices are things like rain gardens, grass swales, infiltration basins, things like that. So looking at the most cost-effective mix to meet both flood reduction goals and water quality goals. I mentioned that land use is changing rapidly in this watershed. They're also dealing with climate change. So we're interested in whether the current optimal strategies will be robust over time, and if not, can we create more robust strategies? And finally, what are the other water quality benefits and non-water quality co-benefits associated with green infrastructure solutions? And do these benefits vary across different neighborhoods or socioeconomic groups? One of the things you can do in WMOST is evaluate the synergies between managing flow, peak flows, or low flows for that matter, and meeting water quality targets. So we actually set up a series of flow targets to try to meet with analysis with WMOST. So at the high end, above discharge levels of 6,400 cubic feet per second, we want to avoid exceeding that target because beyond that, there's likely to be local flooding damage within the watershed. We go down to a third of that, and we have another target corresponding to the 99th percentile of monthly total phosphorus loads. This is important because the water quality criteria for downstream Lake Houston are based on anti-degradation, and so they used the historic time series for chlorophyll in the lake from 1990 to 2008 and found the 99th percentile of chlorophyll values. So we're looking at the corresponding percentile for monthly total phosphorus loads to try to meet that criteria. Downstream Lake Houston is an important drinking water source for the Houston area, as well as a recreational resource. If we go to a flow target half of that, that's where overflow flooding occurs, where you're overtopping the watershed boundary and increasing the probability of exceeding the capacity of the Addicks Reservoir to the south. And then at an even lower target, we're finding water quality impacts, additional water quality impacts. And we looked at water samples collected and analyzed for E. coli, a pathogen, and found that all samples collected at greater than 270 cubic feet per second exceed the recreational water quality criteria. So controlling flows will also help to maintain the safety of residents using the aquatic resources. Second case study I'd like to describe has been completed. This deals with reducing pollutant loads to the Chesapeake Bay. As many of you probably know, the Chesapeake Bay is subject to a TMDL requiring reductions in nitrogen, phosphorus, and sediment. Early on in the process, most of the load reductions were achieved via wastewater controls, but in the stage 2 and stage 3 watershed implementation plans, a much greater fraction of planned load reductions were assigned to urban runoff. We worked in collaboration with the Maryland Department of Environment, Montgomery County, City of Rockville, and the State Highway Administration to identify the most cost-effective suite of stormwater BMPs in this highly urbanized watershed, Cabin John Creek, to meet both the downstream targets for Chesapeake Bay, as well as local sediment TMDLs to protect the aquatic life within the streams of Cabin John Creek. This is the description of the optimization problem. Our overall goal was to minimize costs, both capital and annual operation and maintenance costs for the period 2014 to 2025. We considered a suite of management options, including stormwater BMPs, both gray and green infrastructure, forested riparian buffers, as well as some non-structural BMPs. And we're trying to meet the goals both for the Chesapeake Bay TMDL, 4 to 5% reductions in nutrients and suspended sediment, as well as the more stringent 21% reduction in suspended sediment load to protect the biology in the creek, in the Cabin John Creek. This particular case study was simplified in that we didn't have to meet any water supply or wastewater constraints because the sources and treatment are outside of the watershed and accomplished via interbasin transfers. So we took our inputs to WMOST from the Chesapeake Bay watershed model. We had to do a little bit of additional processing of those time series. In this case, Maryland Department of Environment wanted to find the HRUs based not only on land use and soil type, but also on the responsible party for stormwater BMPs. So we divvied up land that the county was responsible versus the City of Rockville versus the Highway Administration. This is an example of the kind of results you can get. I've actually combined two different results table for this figure. In this case, we're looking at the most cost-effective types and amounts of BMPs to reduce the total suspended sediment loads by 21%. Listed on the left are the potential management practices for stormwater BMPs, and some of these I've also broken down by hydrologic response unit. The second column shows the current treated acres for 2014. So initially, their solutions were focused on extended dry detention basins, a type of gray infrastructure where you're only temporarily retaining water and then releasing it downstream. So you're shaving the peak off the flood peaks, but you're not doing much in terms of water quality improvement. Almost an equal amount of implementation of wet ponds, which hold water for a longer period of time and have more water quality improvements associated with them. When we looked at potential application of BMPs, we looked at site-specific conditions that determined whether or not you could install a particular BMP type and found that there was virtually no area left within the watershed that was suitable for installation of additional wet ponds. And so Maryland Department of Environment was interested in potential for converting dry ponds to wet ponds. The final column shows the optimal treated acres, the change in treated acres under the most cost-effective solution. And I've put arrows by the BMPs chosen to change. So you see a total conversion of dry ponds to wet ponds, as well as a large degree of implementation of infiltration basins and minor implementation of sand filters with under drains. There are a lot of details. I'm just going to sum up the overall results of the case study. Not surprisingly, the total suspended solids reduction targets require the greatest BMP implementation to meet the 21% load reduction. Infiltration basins followed by dry to wet pond conversions followed by sand filters. Maryland Department of Environment actually had a slightly different way of setting and meeting sediment TMDLs based on peak flow targets. And they looked at the relationship between flows and sediment loads using a sediment rating curve. This is important because a lot of the sediments in the system are coming from stream bank erosion. So to meet the peak flow target based on their process, sand filters were most important, followed by infiltration basins, dry to wet pond conversions, bioretention basins, and finally riparian buffers. If the TSS reduction targets were met, then the nitrogen and phosphorus annual load targets for the bay were greatly exceeded with 30% and 40% reductions respectively. If they were only concerned with meeting the more moderate nitrogen and phosphorus reduction targets, riparian buffers would be sufficient and provide the least cost solution. However, they yielded infeasible results for meeting the more stringent TSS reduction targets. We did look at some non-structural solutions as well. For a wet year with more evenly distributed precipitation, street sweeping could affect the necessary reductions in loads, but it was more expensive than other stormwater controls for that particular year examined. For a year with average precipitation that had one large event, however, street sweeping was inadequate to meet the targets. So overall results are sensitive to annual variation in mean and maximum precipitation events, and also the method for establishing the target. And then finally, the third case study is focused on the Upper Soldier Creek in Kansas, which is within the Middle Kansas River Basin. This is a predominantly agricultural watershed, which has TMDLs in place for both E. coli and total suspended solids. Because of the difficulties in modeling E. coli, stakeholders have chosen to use total phosphorus as a proxy, assuming that if they meet the total phosphorus targets, they'll also meet targets for E. coli. They broke down their loading targets into targets for upland loading versus targets for stream bank erosion sources. Again, stream bank erosion is a significant source of both sediment and nutrients in this system. So we compared the optimization solutions for 3 different years: a dry year, an average precipitation year, and a wet year. For the dry year, the targets for the upland loading could be met with existing BMPs in the watershed. For the average precipitation year, grassed swales were the most cost-effective solution for urban lands, and contouring was the most cost-effective solution for agricultural lands. Results were somewhat different for the wet year, with sand filters replacing grass swales as the least cost solution for urban systems, and contouring remained the least cost solution for agriculture. However, when we only considered upland BMPs, we could not meet the combined targets for both upland loading and stream bank erosion sources. So to meet these, the combined target will require flow reductions as well as probably some stream bank stabilization. And we're in the process of testing the success or robustness of current optimal solutions under future climate change scenarios. I mentioned some additional tools to aid in evaluating results and interpreting results. ScenCompare is also built on an Excel spreadsheet. It allows you to import result files from multiple WMOST runs and compare them in tables and graphs. So you can compare management options selected, as well as various endpoints, runoff volume, loadings, etc. We also did some additional development of the scenario comparison tool to create our benefits module interface. This allows you to import multiple run results for nitrogen, phosphorus, and suspended sediment, which are needed to calculate a water quality index. We've also incorporated various lookup tables to allow you to calculate the value of benefits and co-benefits associated with green infrastructure. And I have those summarized in the next slide. So in this figure, the water quality benefits are summarized in the top portion of the figure, and the non-water quality co-benefits are summarized in the bottom portion of the figure. So various management options can be used to meet water quality targets. The changes in nitrogen, phosphorus, and suspended sediment result in changes to recreational and non-use values, which can be quantified using a willingness to pay approach for water quality improvements. If we just look at changes in total suspended sediment concentrations, those can be related to changes in drinking water treatment costs and avoided water treatment costs, and a value placed on those. If we look at a variety of measures that tend to increase green space, these include things like land conservation, green infrastructure, riparian buffers, or increases in urban tree canopy. These tend to improve the aesthetic quality of the landscape, and we can actually quantify estimated increases in residential property values associated with that increase in green space. For a subset of these, land conservation, riparian buffers, or increases in urban tree canopy, we can estimate potential reductions in air pollutant exposure, increased carbon sequestration, and reduced urban heat island effects. The latter is also associated with the implementation of green roofs. These in turn lead to reduction in adverse health outcomes, increase the total poundage or tons of carbon sequestered, reduce power plant emissions, and have associated reductions in heating and cooling costs. And again, we can quantify these as benefits per hectare of tree cover, quantify the social cost of carbon, and quantify associated electricity savings. Results are available for our partners to use in solving their problems. In the first case, we partnered with Maryland Department of the Environment. They're interested in running a series of use cases with WMOST and using the results to inform watershed managements with similar conditions, rather than running WMOST on every single watershed. So we've identified highly urbanized watersheds that have to meet both Chesapeake Bay targets as well as local sediment TMDLs. And the guidance from this case study are available to those parties. For the Upper Soldier Creek in Kansas, we partnered with EPA Region 7 and KDHE, and the results can be used to inform adaptive management for TMDL implementation for Upper Soldier Creek. In the case of Cypress Creek in Texas, we're partnering with the Army Corps of Engineers, as well as state agencies, the Houston-Galveston Area Council, and a local NGO, the Katy Prairie Conservancy. U.S. Army Corps of Engineers is currently conducting a watershed assessment to evaluate existing flood mitigation options. There's another group in the watershed developing an implementation plan to deal with water quality issues, and the results will inform both of those efforts. So overall, we've developed a suite of tools to find the most cost-effective approaches to meet both water quantity and quality goals, starting with the Hydroprocessor to provide inputs to WMOST, ScenCompare to make comparisons across multiple WMOST runs, and finally the benefit module to look at benefits and co-benefits. We found consistently that the most cost-effective suite of practices vary between wet and dry years, so we need to identify robust solutions that will be successful under changing climate and land use conditions. And to facilitate robust decision-making, we have an existing EPA tool called LASSO to define the bounding conditions for future scenarios, as well as HCAM to help generate multiple climate change scenarios in WMOST. And HCAM is not currently available, it's under review. We expect to have that released in late summer. I provided some additional contact information. My contact information is at the top. Chris Weaver has provided resources for the development of HCAM. His email address is here. Phil Moorfield has overseen the development of LASSO. His email is here. And finally, I've given you the URL for our webpage, which allows you to download the tools, user guides, documentation, case studies, and additional more detailed training materials. Thank you, and I think we have some time for questions.